The dawn of 6G marks a transition from terrestrial networks to a truly global, three-dimensional connectivity infrastructure. To reach every corner of the planet, we must look to the skies. This new architecture, known as the Space-Air-Ground Integrated Network, or SAGIN, combines low Earth orbit satellites, high-altitude platform stations, and unmanned aerial vehicles. At the highest tier, LEO satellites form a space-based mesh network. Unlike traditional geostationary satellites, these orbit much closer to Earth, reducing latency significantly. They provide the backbone for universal coverage, ensuring that even the most remote rural areas or maritime routes stay connected to the digital world. The intermediate layer is occupied by high-altitude platform stations, or HAPS. These are semi-permanent, solar-powered aircraft that hover in the stratosphere for months. HAPS excel at providing regional low-latency services. They are perfect for augmenting network capacity in specific areas without the need for massive ground infrastructure. The most accessible layer consists of unmanned aerial vehicles, or UAVs. These offer extreme agility and can be deployed in minutes for on-demand coverage. Beyond communication, UAVs are essential for the 6G vision of joint sensing and communication, providing real-time data for infrastructure and environment monitoring. Analyzing the techno-economics of these layers is vital. While LEO satellites have a high initial cost, their global reach makes them efficient for widespread coverage. UAVs are 2 orders of magnitude cheaper than satellites, but cover much smaller areas, making them ideal for localized, temporary network gaps. HAPS face significant technological and regulatory challenges, including the need for high-performance solar panels and complex spectrum management in 3D space. One of the primary use cases is maritime connectivity. LEO satellites ensure ships stay connected anywhere on Earth, while HAPS can boost capacity in busy shipping lanes. In the skies, HAPS can provide high data rate, low latency connections for aircraft, transforming the passenger experience and cockpit communications. For emergency response, the responsiveness of UAVs is unmatched. They can restore communication services instantly when ground infrastructure is compromised. Network augmentation is another key area. UAVs can alleviate temporary congestion during large events, providing relief without permanent infrastructure expansion. To evaluate these technologies, we look at the total cost of ownership, which balances manufacturing and launch costs with long-term operational expenses. LEO satellites typically have a lifespan of 5 to 8 years. Maintaining a healthy constellation requires periodic replacement of these units. HAPS stations are designed for longevity, potentially operating for up to 20 years, making their annualized cost more competitive for regional services. Operational costs vary wildly. HAPS rely on solar energy with minimal direct costs, while UAV fleets require frequent maintenance and energy management. When scaling to a global level, the investment in thousands of LEO satellites becomes justifiable due to their massive simultaneous coverage area. Conversely, for small-scale scenarios like festivals or stadiums, a swarm of UAVs offers the most economical alternative for high-speed connectivity. One of the biggest hurdles for 6G is dynamic spectrum management in a three-dimensional network, requiring novel ways to avoid interference. This architecture requires unprecedented cooperation between the telecom, aviation, and space sectors to manage airspace and ensure safety. In regions prone to natural disasters, such as tectonic hotspots, HAPS offer a resilient IoT backbone for seismic monitoring and emergency preparedness. National security also benefits. HAPS provide better image resolution than satellites and longer endurance than drones, perfect for remote surveillance. The true promise of 6G is ubiquity, the ability to provide high-speed, reliable communication regardless of geography or infrastructure density. For remote farms and communities, this integrated sky-based network means the digital divide could finally become a thing of the past. With the integration of LEO satellites, billions of IoT devices can be managed from space, facilitating global environmental and logistics monitoring. Latency remains a critical factor. While LEO is impressive, HAPS and UAVs offer the ultra-low latency required for real-time remote operations in 6G. The synergy between these layers is what creates a truly resilient network, capable of adapting to a wide range of spatial and temporal demands. Future ground stations will serve as the glue, linking terrestrial 5G and 6G cores to the expansive capabilities of the airspace and non-terrestrial networks. While challenges remain, the rapid maturation of photovoltaic and battery technologies is bringing the vision of persistent aerial networks closer to reality. The path to 6G standardization involves integrating these non-terrestrial components into the core of the global communication fabric. As manufacturing costs decrease and deployment efficiencies grow, the economic case for an integrated sky-based network becomes undeniable. We are entering an era where the sky is no longer a barrier, but a bridge, connecting everyone and everything, everywhere on Earth. Integrating LEO, HAPS, and UAV technologies is the key to unlocking the full potential of 6G. The future of connectivity is truly taking flight.